again. It's now the GaN question and answer sessions for the first 5 presentations. Thank you to the presenters that you have provided the material ahead of time, and we will have it available by Friday this week on demand on our website for anybody who was not able visiting or watching it actually. Now we are open for questions. The questions come in by mail. I see them on the screen and will forward them to you. Let me start a little bit. We had the SIC session, and we had a question there, which was addressing the difference. What's the difference and what's better, SIC or GaN? And it was answered that it covers different range of voltage class. It has an overlapping class. So I may ask, start with Alex, if you have an idea to explain it to the auditorium, GaN versus SIC.
So, you know, GaN today is the commercial GaN is basically all GaN on silicon, and they're lateral devices. That means the electrons flow along the surface of the device. And it's extremely efficient because there is something called a two-dimensional electron gas, which is very, very high mobility compared to silicon or silicon carbide. However, as you go to higher and higher voltages, lateral devices need wider and wider spacing between the terminals, and it becomes less efficient compared to a vertical device. Now, the silicon power devices, IGBTs and MOSFETs, are vertical. That means the current goes through the semiconductor from the top to the bottom or the bottom to the top, and same with silicon carbide. So as you go to higher voltages, there's a relative advantage towards vertical devices. And I break it down into, I think that GaN has a distinct advantage, both cost-wise and performance-wise, below 650 volts. Silicon carbide has a distinct advantage above 900 volts. And between 650 and 900 volts, it's a battleground. And IGBTs are in there too. So, that seems like maybe a narrow range, but it turns out that's where electric vehicle traction drives are as well. So I think there is a true battleground in there, and we'll see who wins. There's I'd say secondary and tertiary factors that will determine that. Perhaps the most important secondary factor, though, is the fact that GaN is easier to integrate. So you can potentially integrate more functionality onto these power devices in that big range for traction than you can in silicon carbide. But I say it's an open game right now.
Alex, thank you. The first question I get from outside is, when will planar GaN SI technology enter electrovehicle traction inverters, or is this rather something for vertical GaN in the future?
And who's that question for? Is that for me?
Whoever feels, as I think, it will be, as you addressed, in a higher voltage range than what you general covers. But
so maybe I can address it.
Tony, that would be nice if you do it.
Sure. Peter, by the way. It's there today. We already have GaN in traction inverters, easily applicable in the 400 volt battery range, and also in higher voltages already. 800, 900 volt batteries can be done with gallium nitride as well, with what we call a hybrid approach with IGBTs in a T-type converter, where in the high power range, you turn on the IGBTs, but in 95% of the use of the traction inverter for the automobile, the gallium nitride can be operating at a much higher efficiency, and thereby reducing all of the losses. And the nice thing about it is that you don't need to size the gallium nitride for the highest power, because you'll let the IGBTs take care of that, and you can size the gallium nitride for the 95% of the use of the automobile, and thereby reducing the overall cost as well.
Thank you, Peter. I just want to let the auditorium know that question and answer function is at the bottom area, and type in your questions. That's the easiest way to get the questions. And the next question has already.
Excuse me, Bodo, I'd just like to add one little point to that, and that is that
go
GaN
ahead, Alex.
is already also designed into a lot of e-mobility applications where I think there's a big marketplace, scooters and bikes and things like that, which tend to be in the lower voltage range, the 48 to 36 volt range. And I think that's a very fertile market for GaN as well.
Oh yeah, I fully agree to that. My focus when electro vehicles had been addressed here was the mindset was in automobiles, and there we have 400, and even now the people thinking of 800 volt bus voltage, and that's quite a higher voltage, which is still addressable from GaN. The next question: who do you refer to using GaN in traction inverters? And that was addressed to Tony, but I think it's Peter.
Oh, sure, yeah, sure.
Yeah, because we have a name change for whatever.
Yeah, no problem. So I'm not sure I understand the question, but I assume the question is who is using it in traction inverters? And it is tier one automotive companies building traction inverters for the OEMs in today's electric vehicles. I don't think I can go into much more detail than that, unfortunately. But it is
okay.
In
thank you, Peter. The next question is addressed to Mike. The question is how GaN is implemented in Power Integration's new min-E-cap device.
Okay. Well, we don't sort of talk about the details of the technology implementation, but I think one of the things that is clear from hopefully from the presentation that we just watched is that we're seeing the attributes of GaN being applicable to more than just the typical sort of inverters and power supply conversion applications that have been used to date. This is a rather unique use of the GaN, and as I explained in the presentation, there's some key attributes of the GaN that make it applicable in this. It's actually a very low frequency application. It's not by, normally we associate GaN with high frequency. It turns out that the attributes of the GaN are very well suited to, this is a mains frequency, 50, 60 cycle application. So it's implemented there, and it's implemented using our GaN that we developed. So it has internal current sensing and thermal sensing and so on, all of the protection features that are needed for that application. So I hope that goes some way to explain, how it's implemented. And the presentation goes into a little bit more detail on that.
Thank you. The next question seems to me very generic. Which reliability tests are performed within autoqual and test flow? I think
that one's for me. So AutoQual Plus is an enhanced sequence of tests specifically for our automotive grade products, and they go beyond the AEC-Q 101 requirements. So all the AEC-Q 101 tests are performed on the transistors, and then there are some enhanced tests that we've developed with some of the industry leaders. And they include extended high humidity, high temperature, reverse bias testing, some dynamic HTOL, high temperature operating life tests, and some enhanced other tests that we're performing that we really can't get into details on this call, but we'll be glad to share them with you if you contact us, and we can talk about this in more detail.
So, I'd just like to add that I put a link on the answer to a more detailed description of AEC qualification for GaN, in case anybody wants to read it.
Okay, gentlemen, I think Stephen and Denis, you are in areas which are not so much into automotive, but your comment is also welcome.
Thanks. I guess I'd start by saying that we're not in those areas yet, but we definitely have a high power roadmap for going into different things. Actually, going back to Alex's comment, the world of electric traction is not just EVs. It is a host of things: e-scooters, e-bikes. You could even throw in Amazon delivery drones in that whole thing. So there's a broad range of voltages for different batteries, different range of powers. So it's a very fertile area, and I think for GaN overall, it's an excellent new area to kick out silicon.
Okay, the next question. Why chose GaN over SiC in electric vehicle traction inverters? What are the technical and commercial pros and cons for both?
Do you want to take that one?
Sure. Okay, so it comes down to performance. So it's going to be lower switching losses, very low conduction losses, and you'll have the ability to get to even higher frequencies in silicon carbide, so you can switch the motor at higher speeds and reduce the overall size. So it really comes down to performance at this point. So, and from a commercial perspective, remember, gallium nitride is GaN on silicon, so it starts with a silicon wafer, available in abundance. It doesn't have any capacity constraints, and therefore there's a security of supply element to it, and of course it's much lower cost than a silicon carbide wafer. So I think there are both the commercial and the technology is there in favor of gallium nitride in traction inverters. There is some silicon carbide applications that make sense in the very high voltages. Above 1200 volts there's fertile ground, but below that, gallium nitride wins.
Thank you. The next question I come up with here from a visitor. When will we see mass production and higher market share for GaN in industrial applications?
So as you know, we've been in production now for 11 years in this coming March. We make millions of units per month. So I'd say that mass production's been around for several years. Industrial applications tend to be a little slower because they are, and rightfully so, very conservative. But I think we've been on cars now for since 2011, so that's almost 9 years. It is 9 years that we've been on vehicles, which is probably one of the most difficult applications. And also, we've been in space for many years, which is even more, I'd say, in many ways more conservative than industrial applications. In industrial applications, automation, motor drives is a good application. It's in the medium volume range right now. I think it'll go to high volume over the next few years. So that's where we see the biggest thrust. Also robotics, which I don't consider industrial, but robotics is another big area.
Thank you, Alex.
Yeah, if I could perhaps comment as well a little bit. As I mentioned in the presentation, we have over 80 customers in production. With our GaN, of course, is all high voltage. So we have 750 volt devices, mostly used in switching power supplies. Although with the new mini cap, it's a slightly different application, but still using the high voltage GaN. And so, yeah, we've seen very broad adoption. Initially, of course, as you might expect, very small adapters, AC/DC adapters, and so on. But more and more, we've seen customers come to using our GaN products in any number of different industrial applications, from meters to other applications. So yeah, we've seen very broad adoption, and we've again been in production for several years now. So we think it's already happening, actually.
Yeah, there's a big takeaway also from different voltages, as Mike and Alex have said. Obviously, Alex has pioneered the 48 volt input brick, whether it's an 8th brick or a 32nd brick or a 64th. Examples like Density Power in China using Navitas GaNFast in a 400 volt input DC-DC quarter brick. So that's just another example of how traditional applications using silicon, we're now getting 2-3 times the power density as a first step using GaN. So we'll see continued improvements into all these areas of the industrial market.
Yeah. If I may add on the demand of GaN, actually we provide technology, let's say, different than all the other people here, and we really see an increase in demand of company with an 8-inch fab looking for sourcing technology for us because they want to produce GaN, showing a clear big demand and of volume, let's say. So I think I share the opinion that is really happening right now, the mass production.
Thank you. The next question is to Mike, that the question is that GaN can be used for non-high voltage apps. Can he expand on that? The question is, as I understand, what's the high voltage range? There is the question, what is high voltage? And I will bundle it with the next question. Will GaN be there in the 1200 volt market, or are those applications left to SiC? I think that's the same direction.
Okay.
Both questions.
Well, to the extent that I understand the question, so our GaN technology is what we refer to as high voltage, as I mentioned, 750 volts. As we just talked about, I think Alex has pioneered the lower voltage end of that market, and of course all of the panel members have different products at different voltage ratings. So ours is very much focused currently on 750 volts, and the application of those within our products is a combination of what we call single-ended switching converters, like flyback converters, where the voltage applied to the devices is higher because there's a switching aspect to the operation of the device, so it sees voltages above the input voltage. It's not like an inverter half bridge. It has reflected voltage and leakage spikes and so on. So, but even in the application of the minicap that we presented today, where there is no, switching spikes as such, no inductively, stressed switching spikes, we found it's very effective there because of things like line surges and swells, certainly in areas such as India, where we see very, very high AC line voltages. So I think our application of the GaN we're seeing very broadly, not just in traditional switching converters, but in applications such as the minicap. But I think the lower voltage, maybe Alex is better to comment on its usage in those areas. And then just finally, the question about 1200 volts, as we've already talked about, I think that's definitely the battleground between things like GaN, SiC, and IGBTs, depending on the application. But we certainly see a home for GaN at 1200 volts in the future. I think that's definitely coming. And the fundamental benefits of the GaN technology in terms of the low-cost starting materials definitely seems to have an advantage there. So we think GaN will have a place at 1200 volts in the future for sure.
Yeah, so if I could add in here, I think that we're seeing GaN's big advantage in volume right now in DC to DC converters for servers. I'm showing in background here a volume application that's going into high-end servers all over the world and multi-sourced. But at 48 volts, GaN has a distinct advantage over silicon in every performance characteristic, in size, in thermal performance, and in cost. So, it's really sweeping. And if you look at 48 volts, it's a very important node in that people are going to 48 volts on board on servers, but also hybrid cars are going to 48 volt buses, and there are motor drives at 48 volts. Many drones and robots now are running at 48 volts, particularly at the higher ends. So this is a big market. I think this today is probably the biggest market for GaN out there.
Thank you, Alex.
If I may, I'd like to reiterate what Mike said. There's clearly a play. 1200 volts will not be left to silicon carbide alone. We will be in that market. It's coming. In summary, you can look at the different applications. If you can use silicon MOSFETs, it makes sense. Those opportunities are going away with the need for higher efficiency and smaller size. Alex has proven that. There's areas for silicon carbide when you get to the very high voltages, as I said, above 1200 volts, but below that, it's really GaN. So use silicon if you can, use silicon carbide where you must, and use gallium nitride everywhere else.
Yeah, regarding the high voltage, we are also looking at that more in the longer term perspective. So there is a big push from the industrial players that work with us to go under actually beyond 1200 volt or toward 1800 volt. And they need this because they want to have a platform that range, let's say, based on GaN, the range from low voltage application up to very high voltage application. So this will not be necessarily GaN on silicon, but there is a clear demand to cover a wider range with one material, let's say. Yeah.
Gentlemen, I don't see, no, I see the next question coming. Are customers interested to replace silicon by GaN in data center applications?
Yeah, and I think the answer is yes, as they go from 12 volt buses to 48 volt buses. The 48 volt down LLC converter is an extraordinarily efficient way to get from 48 volts down to lower voltages. So we're seeing two trends. One is go to 48 volts on the board. Even in notebook computers, we're seeing 48 and 56 volt conversions. And then from there, go down to a distribution bus. And on servers, we're seeing more frequently that rather than using 12 volts distribution, they're going down to 5 volts or 6 volts. And then they're using a BCD MOS 6 volt to 0.6 volt POL. So getting from 48 volts in a 10-to-1 ratio down is really incredibly efficient with GaN. At a megahertz, you can get 98% efficiencies all day long. You know, this is a very large and very quickly developing application. My prediction is that, you know, for servers, they'll all be 48 volts down to bus voltages down in the 5 and 6 volt range. For notebook computers, as we go to fast charging, thanks to the pioneering work of Navitas, you know, everybody wants fast charging. They're going to much higher powers going into the computer for fast charging. And that means that they've got to use about 59 volts into your notebook computer to get enough power to really charge the thing up in a few minutes.
Thank you,
Very good.
Alex. The next question is,
Bodo, could I add
okay,
on to that?
Stephen.
And maybe actually jump to the next question. Yes, I agree that the 48 volt hub, whether it's for automotive or industrial or servers, is key. Obviously, we've got NVIDIA, when they made the switch from 12 volt input to their GPU cartridges to 48 volt, that was a major watershed moment that came a couple of years ago. So I think 48 volt is the way of the future. Also, the consolidation of the hyperscale data center rather than smaller discrete data centers. I think 48 volts will also win because it's a clean piece of paper scenario for edge data centers when we get to autonomous driving as well. So I think 48 volt will be a big hub. Moving to the question about AC-DC, we've actually had GaN in AC-DC server units since 2017 when LTEC, now part of the Delta group, released their, can't remember the code name for it, but it's a very high efficiency AC 3 kilowatt unit going to 48 volts. So GaN's actually been in that market for about 4 or 5 years. We've also had Bell Power and a few other companies do that as well. So there's a big spread of GaN already in the data center, and it's all down to power density. You can get with the platinum Energy Star rating, you can get some silicon devices with very high efficiency, but they tend to be big and you tend to have to blow a lot of air through it. So if you can go
we come to an end. My last question I have here is, how about AC/DC applications? I think that's something which is in the, depends what voltage class, if we use the AC in the US or the AC in Europe. But Mike, that's something.
Yeah, I mean, exclusively all of our GaN products are used in AC/DC converters. And, you know, the thing that we're seeing more and more is we're just increasing the footprint within those AC/DC converters. So we have products like InnoSwitch that I talked about in the presentation for the main flyback stage. And now we have products like MiniCap, which is another GaN in the AC/DC adapter. So actually what we're seeing is multiple GaN devices in AC/DC power supplies going forward, as opposed to just one. So it's ubiquitous in all of our AC/DC converter products now and into the future.
Thank you, Mike. Thank you, gentlemen. We continue with the presentations, and it was great to have you all on stage. And it's a pity that we cannot have it in reality, but it worked fine out in virtual conferencing. Thank you.
Thank you, Bodo. Thank you, Holger.
Thank you,
Holger
Bodo.
behind
Thank
the
you very
screen
much.
there.
Yeah.
Thank you very
Thanks,
much.
everybody.
Everyone.
Bye-bye.
Bye.
Bye-bye.
Thank you. Bye.